Professor Sarik, I was just curious. So why did you have three different links? Didn't it? You had to switch
Sir,
over, right?
sir, actually, many times we had such experiences that one link doesn't actually work for the complete FDP.
Mm-hmm.
Uh, and also, we get a separate recording for the. We, as soon as we are out from that meet, we will get a recording automatically.
Right.
That is one of the reasons. And there are many other issues which crop up if we have only one for
Mm-hmm.
all the sessions. So we have not done 15 links, but three.
Okay.
And I was able to come to the next link immediately. And
Right.
even in parallel, I can do if people really. This is what I announced in my last meeting that I will not be very fussy about the attendance. That is true. So it is about learning.
Mm.
So those who will wish to learn will automatically join in
Right.
time. So let us wait for next 3 to 4 minutes.
Okay.
Actually, for me also, I felt short of time and not short of time, very short of time.
Mm.
So I could complete only half of the collection I made for this particular FDP. And
Okay.
rest, yes, rest was already in fact covered in the previous slides only. So
Okay.
I did it fast in the last 20 minutes.
Okay.
That is why I'm a bit worried. It is 11:50. Okay, 3 to 4 minutes. Let us wait.
Okay. Yeah, sure.
Yeah. Yes, sir. I think we should start the session
Okay.
because it is already too long.
Right. Right. Sure.
So I will like to read a very brief profile of yours, sir.
Sure. Sure.
Uh, uh,
Okay.
Dr. Raghav Mutharaju is an assistant professor in computer science and engineering department of Triple IT Delhi, India. He got his PhD in computer science and engineering from Wright State University, Dayton, USA in 2016. He has worked in industry research labs such as GE Research, IBM Research, Bell Labs, and Xerox Research. His research interests are in the various aspects of semantic web such as knowledge graphs, ontology modeling, reasoning, querying, and its applications to specific domains. He is also interested in big data applications. He has published at several venues such as I also told in my PPT, ISWC, ESWC, ECAI, and WISE. These are those conferences. He has co-organized workshops at ISWC 2020, WWW 2019, Website 2017, ISWC 2015, and tutorials at so many workshops. He has been on the program committee of several semantic web conferences such as AAAI, WWW, ISWC, ESWC. Again, the same flagship conferences are listed here. Most information is available on his homepage, which you could easily get on Google. So over to you, sir.
Right.
Thank you so
Thanks.
much for joining.
Yeah, thank you. Thank you, Professor Sarika ji, for the introduction as well as for inviting me to give this session. Uh,
That is our
so,
pleasure. Please
yeah,
go ahead.
it's great. So, yeah, hello all. Hopefully, you had a good sessions so far, and please feel free to interrupt me at any point of time if you have any questions, and then we can have a discussion. Right. So in this session for next, let's say 1.5 hours, I'll be talking about ontologies. So what are ontologies? And then how do we build them? So in the first half, I'll briefly talk about these aspects. So why do we need an ontology, and how do we build an ontology, and what is an ontology? And in the next half, I'll be, so it's a group activity, right? So we'll all be building an ontology together using a tool called Protege, right? So that's the plan for the session. So let's get started. So have you heard about this term, knowledge representation and reasoning? So we can keep this interactive. So if you have any thoughts or comments to make, please unmute your mic and then uh, you can talk, right? And the other thing, okay, I heard a ping, but so I'll not be looking at the chat because I have only one screen, right? And I'll have to look at my just one screen. So I'll be looking at the slides, but if you have any comment to make, please unmute and talk. Okay, so let me go ahead. So one of the important differences, so to say, between man, machine, and even animals, as they say, is the ability to gather knowledge and then use that knowledge for inferences, right? To draw some inferences. So this is so we generally put all these things under the category of, say, intelligence or thinking, ability to think and reason, right? So this is an important difference, and this is what supposedly makes man more, to use the term, intelligent than the other species, right? And one of the important components that helps in this case for us to become intelligent is this process of gathering knowledge. So we can gather knowledge from a variety of sources and means, right? So for example, we gather knowledge by observation, which we have been doing since we were born, right? So we look at things, we look at others, and we learn from what is going on around the world. And the other mechanism is obviously books and reading and attending these kinds of sessions where you read books or learn from others, watch videos. So these are different mechanisms to gather the knowledge, and we'll be making use of this knowledge at different points of time. So let's say whenever you are asked some question or whenever you are asked to make a decision, let's say for example the decision to attend this FDP or not. So you will be thinking about it, and you will also be using your knowledge. You will be consulting your colleagues, and based on all this information, you will be making a decision. Right. So there is some background knowledge, and you are also drawing some inferences or additional knowledge out of it. So this is what is called as knowledge representation and reasoning. Right. So there are two aspects to it, which we. So the first part is the knowledge representation part, and second part is the reasoning part. So it's called KRR in short. So in the knowledge representation part, we'll be talking about the techniques to gather the knowledge and then make it in a or keep it in a format that people can. So in this case, it's the machines. So all this is meant for the machines, right? So the idea behind this subfield of AI, which we'll see in a minute, is that machines can also make use of the background knowledge that we have access to, right? And then based on that background knowledge, they can try and take better decisions than they were earlier if they don't have access to this knowledge. So an example is this car, right? So whenever I tell you about a car, for example, I'll tell you that I'm looking for a new car to buy. And then whenever I say these terms, car, you know what a car means, but a machine would not understand what a car means. So for the machine, it's a sequence of characters. So like C followed by A followed by R. So it's a string. Right? But for you, it's different, or for all of us, it's very different. Right? So whenever someone says there's a car, immediately say for example, the picture of the car flashes in our mind, and we begin to think about some of the characteristics of a car or features of a car. So things like car is a type of vehicle, or car has exactly 4 wheels, like the cardinalities, right? So we can look at these cardinalities here. So car has at least 2 doors and at most 4 doors. So these are the kinds of things that we already know about car, and we can associate these things with the car, but a machine cannot. But using these knowledge representation techniques, we can capture these sorts of knowledge also, and machines can make use of it. Right? So the second aspect of this area or subfield is the reasoning aspect. So again, it's very easy for us to draw inferences. So an example of one such inference is given here. So let's say you are presented with 2 facts. One is all birds fly, and the second one is pigeon is a bird. So based on these 2 facts, if you are asked the question, can pigeon fly? You can deduce the answer, right? So you already know that pigeon is a bird, and you also know that birds fly. So pigeon should also be able to fly, right? But if you ask the same question to a machine, so if you give these 2 facts, and if you ask the machine, can pigeon fly? It will not be able to answer. So unless you explicitly state that pigeons can fly, it will not be able to answer, right? So how can we make even machines to infer knowledge or these kinds of facts based on existing knowledge? So those mechanisms come under the category of reasoning. Right? So these 2 aspects, they help with the, like I said, gathering the background knowledge and then making some inferences on top of it. So this is what is this helps in making these agents. So agents are any software agents, or say robots, which we, or any machine, for example. So they can make use of this background knowledge or this subfield and then take better decisions. So that's the whole point of this sub area. Right? So you might have heard of a lot of other subfields. So nowadays the learning aspects are very popular, right? So but apart from that, there are many other subfields of AI which help in making machine more intelligent, or it will try to make machines mimic the behavior of humans, right? So that's the whole point of AI. So you have subfields like planning and natural language processing, which you would be aware of, and then you have this learning. So learning, again, there are aspects such as you give some examples, and then machines can learn from those examples and try to make a decision, right? So there are things like computer vision, robotics. Again, so these days is artificial neural networks. So one of the other subfields is, like I said, is knowledge representation and reasoning. So whatever you will be learning across these 5 days, right, in the FTP. So all these things come under the broad category of AI. Okay, so I'll move on now. So although we'll be talking about ontologies in this particular session, that is not the only mechanism to capture the knowledge. There are lots of other mechanisms, but like I said, in this session and across this entire FTP, we'll be talking about ontologies and knowledge graphs. So we'll briefly discuss that, but I think it will help just for the historical reasons that there are other mechanisms as well. So one of them is called frames, and the other one is called semantic nets, and there are a few logic based, so by logic based formalisms such as first order logic, description logics. So these two form the basis for ontologies, right? Although we will not be looking at these two things, but you might most likely be aware of first order logic, right? And description logics is a subset of first order logic. And ontologies, so whatever we learn here, so it is so it comes under the broad, I mean, there's a language called OWL or OWL, right? And the full form of that is web ontology language. So we can use OWL to create these ontologies, and OWL is the underlying theory behind OWL is description logics, right? And description logics is a subset of first order logic. So that is how all these are connected. And RDF is again, you will be hearing about RDF when you attend these knowledge graph sessions, right? And I'll also be talking briefly about RDF in this session and later on in my other talk, which is on the last day. Right. So these are all mechanisms to capture the knowledge and in a structured format and using some formal mechanisms, right? Okay. So now, let us start with the ontology part. Again, so I'll briefly discuss the historical perspective and then come to the perspective from which we'll be looking at. We meaning the computer science folks, right? So ontology as a term, it's pretty old. So it's actually centuries old. So it comes from philosophy, and you might have heard of these famous philosophers like Aristotle and Plato, right? So they were the ones who started using this term, and they coined this term, and then they, in at least in philosophy, it's mainly used for the study of being or existence. So it's mainly used for discussions. So, for example, I listed a few examples here. Right? So, what are the things in the world? What are the important things in the world? How are they related to each other? And how can we categorize different things in the world? So, study of different things or a being. So, being can be anything in the world, right? So, study of different things and how do we categorize them? How do we get to know more about them? So, this is what is called as ontology. And so even in computer science, it's pretty similar. So except the major difference is that the ontology is developed in computer science, especially using this OWL language. So they are meant for the machines primarily, right? I mean, even humans can look at it and then they can get good idea of the data and underlying domain. But machines can also work with these ontologies and use it for their decision making. So there are a couple of examples. So there is no one standard definition of what an ontology is in computer science, but there are few of these well-known definitions that I'll be going over. So the first one is by Gruber, and he states that ontology is a formal, explicit specification of a shared conceptualization. Right? Okay, so there are many. There might be many new terms here, so I'll be going over each of these terms. And if you have any questions, like I said, you can stop me at any point of time, ask the questions. Okay, the first term here is the formal. So by formal, we mean that we need to use any formal language. Like, so in our case, it's first order logic. So the importance of using formal languages, all the terms and vocabularies in that language are well defined. Right? So for example, when you say conjunction or disjunction or implication in first order logic, you already know what this means. And there are lots of tools that can understand what this means. And it's not ambiguous. Right? So when you say car, for example, car has two wheels or something like that, then there could be some ambiguity in the sense that, for example, the same word in different contexts can mean different things. But car obviously doesn't fall into that category. But if you make use of any formal language, it's very explicit what you mean. So that's the advantage. And the second one is explicit specification. So you explicitly give out the concepts, the important concepts in the domain and the relations between them. Right? So they are well defined, and there's nothing that is sort of implicit or ambiguous again. So the third keyword here is the shared part. So by shared, we mean that this ontology, it's a shared view. It's a shared understanding across several different people. So generally, the way to build this ontology is to talk with these domain experts, right? So let's say you are building an ontology in a healthcare domain. So the best way to build that is to talk to a doctor, because the doctor is the domain expert, obviously. And let's say you are the computer science person. So you can develop the ontology, but it should be developed in consultation with the doctors. Right? And ideally, a few people come together, people who are working in similar applications or similar domain, and they discuss what concepts are important in that particular domain, what concepts should be put into the ontology, and they agree to have this common vocabulary. So that's one of the advantages of having an ontology, right? You will now you will get a common vocabulary for discussions and for sharing with others as well. So, and the last part is the conceptualization. So it should be a simplified view of the world, right? So it should be at an abstract level, so that you get a high level overview of what the concepts and relations are in a particular domain. So if you want to, you can dig deep, you can go deeper and then build more lower level ontologies. But to start off with, it's good to have an abstract level view and then go deeper. So that's the conceptualization part. So these things, they make up or they define what an ontology is. Okay, there are a few more definitions. So there's one more, which is again well known. So this is given by Michael Ushod. Hopefully I got the name right. And then this Gruninger, right, or Gruninger. So this is a simplified definition. They state that ontology is a shared understanding in a particular domain. So again, we talked about this previously, right? So ontology, it has to be a group activity, and then you talk to the domain expert and then build the ontology. So in that sense, it's a shared view of the world. Okay. So that's the definition of ontology, but let's look at some of the different aspects of the ontology, right? One of them is the perspectives part. So if there are different people who are building the same ontology, let's say there are 5 groups, we divide you into 5 groups. And if we ask all of you to build the same ontology, which is on, let's say, university, right? Each one of you would be having different perspectives, and you will be building your ontology according to your perspective, right? So, okay, given this picture of pizza, so what are your thoughts? So maybe some of you can unmute your mic and you can let me know. So what is it that you that immediately comes to mind when you think about this pizza?
It's a food item.
Sorry, what is that? It's a
food item. It's a food item.
Okay, okay.
Yeah. So it's going to be baked using some cheese and some toppings.
Okay.
Like some making material we are going to get in our mind. It's going to be. And
Right,
about taste we'll get, okay, so it's going to be some, okay, so a delicious one and a spun kind of thing. Such kind of
right.
information we are going to get into our mind.
Okay. So are there any other, so this is one perspective. Are there any other perspectives?
Not healthy.
Okay. So yeah, so this, from the health point of view, yeah, that's the other perspective.
It has some round shape and some toppings on the verb.
Right. Okay. So that's about the shape, geometry, right? So okay.
Cost
So
wise more.
crust is more okay.
Italian
So
food.
right. So these are different perspectives, right? And um, so I'll also list out a few perspectives, a few different perspectives, right? So fun. So one is like one of you said, it's an Italian cuisine, and you immediately think of, so if you have tasted pizza before and if you have some opinion on it, you either, for example, if you like it, you will say, okay, this is an Italian cuisine and I like this, right? You'll now, maybe you'll also think about the different cuisines that exist. So for example, there's Italian, Mexican, Indian, and so on, right? And uh, one of you also talked about the crust and all, right? So whether it's spicy, uh, what are the toppings and so on. So these is one perspective. The other perspective is again, one of you said, talked about it. So if you are looking at it from the cook point of view, so if you like cooking, then whenever you see something, you might start thinking about the procedure or the recipe to make it. Right? You may want to go back and try it at your home. So you will think about the recipe. So what is the recipe? What are the ingredients? So whenever you are eating something, maybe you will try to figure out the ingredients that make these pizza, right? And then you will also think about the cooking utensils. What kind of, how much time would this take, and so on. So that's the second perspective. And the third one is, again, one of you talked about this unhealthy or the health point of view, right? The calorie conscious point of view. So whenever you look at these different food articles, you might be thinking about how many calories am I putting in my body. So if there could be more calories or less calories, and so you may want to control the number of calories that you put in. And you may want to, so like we discussed earlier, you categorize these things, right? So we now have three different categories. So one is from the category of the cuisine. The second one is from the category of the different dishes or the recipes, and the third is the calories, the amount of calories that it has, right? So these are the different perspectives, and even like I said, when we ask you to, when you create an ontology, you will be looking at it from different perspectives. So you will be creating an ontology that is suitable with respect to your application, right? So in the university example that I mentioned earlier, so one of you might be looking at it from the course or teaching perspective, right? You will be talking about the courses, the students who are enrolled into that course, the faculty who are teaching these course, and so on. Someone else might be looking at it from the administration point of view, right? So who is the, for example, there's a director for the institute, and then there are several deans who are part of the institute, and then there are administrative staff, and then there are teaching staff. So all these make up the administrative part. So you can also look at it from other angles, like say like the buildings, the classrooms, the facilities in a classroom, and so on, right? So there are the modes of teaching. So nowadays it's online, but earlier it used to be in class teaching. So these are the different perspectives, and they are all talking about university, right? But from different points of view. So that's why building an ontology is not a unique activity, right? So for example, if, like I said, two groups may not build the same ontology, even though they are talking about similar things, right? So that's why all these definitions now, hopefully they start to make sense to you, right? Um, so that's why it's important for some people to come together, talk with domain experts, and then build. And most important thing is, at least the ontologies built using out, they are machine processable. Machines can take the help of these ontologies and then try to make better decisions. Okay. So let's briefly look at other modeling techniques. So again, ontologies are not the only way to model things. There are other techniques, other modeling techniques that you might be aware of already. So we'll briefly look at those techniques and then try to compare ontologies with those techniques. Right? So I'll be looking at two of them. One is the entity relationship diagrams, and then the other one is the UML, which stands for Unified Modeling Language. So again, you can use these modeling techniques as well, but there are some differences. So you might be familiar with ER diagrams. So whenever you this this is pretty familiar in the database world, right? So whenever you are designing some tables, so the first thing that you do is to try to figure out what should be the tables, what are the relationships between these tables, what are the attributes for each of these tables, the keys, and so on, right? So all these make up the entity relationship diagrams. So so again, there are a few important differences between ER diagrams and ontologies. So even in ontologies, you have these concepts and the relationships between them. But in ontologies, a relation can stand by itself. So for example, you can just say has son and leave it at that. But in ER diagrams, that is not the case. So relation has to be associated with a entity or two entities or three entities. So for example, you can say that has son and son of are inverse of each other, or has son is a subproperty of has child. So everything you can have relationship oriented ontologies, right? So there can be properties or relationships which are central to it, but they need not be associated with any concepts. So I gave a few examples, and then the other important thing is you can have more complex things modeled in an ontology. So an example is the uncle relation. So my father's brother is my uncle, right? So if A has father B and B has brother C, then A has uncle C. So it's a complex relation, and you cannot model this in ER diagrams, but you can do so in ontologies. And so the other important difference, which is common across both ER diagrams and UML, is that it is machine processed. Machines can read it and they can try to make some sense out of it. But in ER diagrams, it's not possible. Okay. So next one is UML, which stands for Unified Modeling Language, and it is mainly used for modeling software systems, right? So if you are, let's say, building an application, so before you start building the application or before you start coding, you gather the requirements, and then you try to model that, build a model for this based on these requirements, right? So what should be for example, the classes. So if you are going using object-oriented programming style, then you may have to think about the classes and then the operations that are part of these classes and how do different classes interact with each other, and maybe the flow of the data as well. So for example, given an activity, how does which class takes the responsibility for that, and how does the flow of responsibility happen, right? So all these things are captured in UML diagrams again, but these are not these cannot be captured in OWL. It's not easy to capture the flow and model these different activities. So each of these three different mechanisms that I just mentioned, it has its own pros and cons. And okay, there is what I say in the next slide. So, and it depends on the application at hand. So what is the type of application that you want to build, and based on that, you can select the modeling technique that you want to use. Then go ahead with that. Right. So again, so we looked at two different perspectives. One is the philosophical side of ontologies, and then the computer science of it. So there are some differences, but this is a term that has been, like I said, borrowed from philosophy, and the principles remain the same. So, for example, but the users are slightly different. So they were in philosophy they are mainly used for debates or discussions among the people. But on the computer science side, it's used for machine processing by machines. Okay? And it's generally abstract. They are described at an abstract level in philosophy, but it can be both abstract and specific here. Okay. So are there, let me pause a bit, and if you have any questions, I can take it. If not, I can go ahead. So are there any questions so far?
Yeah, I think I'm not able to see any queries, sir.
Okay. So then, okay, I'll go ahead. So I'll briefly discuss the differences between ontologies and knowledge graphs. Right? So you'll be learning more about knowledge graphs starting from tomorrow, I think, if I remember it right. But across the next 5 days, you will be learning more about knowledge graphs as well as ontologies. So let me just point out some differences, or maybe I should first start with what is a knowledge graph, right? So, okay. So knowledge graph is a graph, as the name says, it's a graph. But one of the key differences is that each node in the graph. So, like you all know, graphs would have nodes and edges, or vertices and edges, right? So one of the differences is that these edges are labeled. And the second important aspect is that each node will have a type associated with it. So, for example, I can say Raghava works at IIIT Delhi. So here you can think of Raghava as one node and IIIT Delhi as other node in the graph, and the edge between these two nodes is work set, right? So that forms the small graph with two nodes and one edge, right? So now you can associate type information with both the Raghava node and IIIT Delhi node. So you can say that Raghava is a type of faculty and IIIT Delhi is a type of university, right? So this type information comes from these ontologies. So in ontologies, you try to discuss things at the abstract level, where you talk about the general concepts, right? So you talk about universities, faculty, courses, but in knowledge graphs, you talk about the what is called as instance data or instance level data. So Raghava is a instance of faculty, right? And IIIT Delhi is an instance of university. And for example, semantic web is a instance of course. So if I teach semantic web, right? And it's an instance of course. So all the instance level data is generally part of these knowledge graphs or RDF graphs, whatever you want to call them. And the high level conceptual data is part of the ontologies. So if you take an analogy of relational database systems, right? So you have your tables and ER diagrams. So ER diagrams talk about the concepts or the entities and the relations between them, and the specific data is part of the tables. So you can have the same analogy here, right? So that's the knowledge graphs. But like I said, you will be learning more and hearing more about these knowledge graphs in the other parts of the other sessions. So I'll not be talking about these knowledge graphs. Okay. So then the next question that might come up is, why build these ontologies at all? So I briefly mentioned this at the beginning of the talk, right? That we need these ontologies to capture the knowledge, and that in turn will help in making better decisions by the machines, and also to infer these facts. So that's one purpose of the ontology. So you can clearly define what you mean by a specific term, and then it can also be used for exchanging this knowledge. So let's say you are building two applications, but these applications are using similar knowledge, right? Let's say it's a healthcare application on any specific disease, like related to, say, cancer. So both applications are related to cancer, but they're looking at two different applications, but they need the knowledge of cancer. So since they need the knowledge of cancer, you can build an ontology, and then both these applications now can make use of this ontology. Let's say there is no ontology, right? Then you would be putting in all those domain knowledge inside your application. And now that knowledge is buried inside the application, right? So you cannot take it out and then use it with another application. So it's useful for exchanging this knowledge. So it works in the same way as, an analogy is configuration files. So if you put your configurations within your code, somewhere deep in your code, you cannot customize it well. And you cannot, for example, so different people might have different type of configurations, right? So it's hard to configure if you are putting it somewhere inside the code. So you cannot, but if you put it out, then you can easily configure it and you don't have to touch the code, right? So in that way, you are trying to take this domain knowledge outside of this application and then make it shareable with other applications also. So that's the first part. So second part is about the reasoning, which we have already seen, right? So this is the same example, but let's say another aspect here is finding these inconsistencies. So let's say you derive this inference, which is penguins can fly, but let's say after 10 days you add someone else in your team, not you, right? So you added these two facts, and someone else in your team has added a third fact, which is penguins cannot fly, which is true. There are always exceptions, right? So this is an exception. So someone added this this fact that penguins cannot fly. So now your knowledge base is inconsistent, right? On one hand, you're saying that penguin is a bird and all birds fly, so penguin should fly. But later on, there's also one more fact which contradicts this fact, saying that penguins cannot fly. So if it is a very large knowledge base, right, it's hard to figure out what are the inconsistencies and if at all there is an inconsistency. So, and this reasoning process makes this easier to first figure out whether there are any inconsistencies. And if there is an inconsistency, then it will also try to, it can also give out the reasons for the inconsistency. So the software that can do all these things is called a reasoner. So we'll be briefly looking at it in the next part. Hopefully there will be time for showcasing the reasoner and all those things as well. Okay. So that's one advantage. The second advantage is it can be used as a documentation also. So let's say you are given this file. It's a CSV file, and there are a bunch of numbers. There are columns and numbers in each column. So unless you are a domain expert, right, you would not be able to figure out. So there'll be names obviously associated with each column, but even those names may not be explicit, right? They'll be ambiguous, or there might be short forms. So unless you are a domain expert, you cannot make sense of it. Let's say there is a CSV file in the healthcare domain or aviation domain or oil and gas, right? So there are multiple different domains. And unless you are a domain expert, it's hard to figure out what these labels mean and what these numbers mean. So, but if you can build an ontology, then you can talk about the relationships between these columns. So for example, one of them is a weight column, the other one is a temperature column, the other one could be the price column, right? So you can talk about the relationships between these columns at an abstract level. So you can say that there's a concept called person. Person has an age, person can have temperature, weight, and so on. And there are relationships between these concepts. So there is a date time concept. So all these, so now when you look at the ontology, you will get an idea. So let's say there's a team of members. Let's say there are 5 people in a team, right? And this is a software team, and they're building an application. So when now they have, after working on this application for some time, they have become domain experts, and they can easily figure out what this file means. But let's say there's a new member, teammate who joined this team, a 6th member, right? Now for the new team member, it's hard to figure out what this file means. But let's say if you give this ontology to this new team member, this new team member can now easily go over the ontology and then figure out what are the high level concepts and relationships between them. And now when he or she looks at this data, they can easily figure out, right, what the data means. So in that sense, it can also act as a documentation. And you can visualize these ontologies. So this is one of the visualization mechanisms. There are other ways to visualize it. So here the concepts are ovals or circles, and the labels on the edges are the properties. And these boxes, they are the data types, right? So for example, here, here this indicates that student is a subclass of person. So every student is a person, but not the other way around. So every person is not a student, right? So student is a subclass of person, and student has a roll number. A person will have a first name and a last name, which are strings. And in that way, you can easily visualize it and then get to understand the domain better, right? So those are the important applications or reasons to build an ontology. And so this is a important again line which I didn't cover earlier. So ontologies are models, right? And models are declarative in nature. So whenever you say something is declarative, it means it's independent of the implementation. So there are multiple ways to implement it, which you are not concerned about. So to give an analogy, right, SQL or SQL, I mean, I think most of you will be familiar with SQL. It's a query language for relational databases. So in SQL is supposed to be a declarative language. So you specify, for example, that you want all the records for a particular course in a particular year, right? But you don't explicitly state that go look at this file 1 and then retrieve records 1 to 100. So that is very specific, right? So when you write, say, Java code, that is implementation specific. But when you just specify the what should be done, but not how it should be done, then that's the declarative part. So here you're only saying that you need the records from 1 to 100, or say 20 to 50. But you are not bothered about how to retrieve those records and how to store these records and so on, right? So that is implementation specific. So in the same way, ontologies are declarative. In that sense, they are declarative in nature. Now, what you do with ontologies and how do you use it? So that is implementation specific or application specific. Okay. So there are a few references that will help you. So if you want to know more about ontologies, I recommend going over these references. Maybe I can, I don't know if, I can share the slides with Dr. Sarika, and maybe she can share it with all of you. And you can go over these slides, right? So that is the first part. So there are a few more slides, but I'll be going over it while building the ontology. So this is the first part where I discuss about what an ontology is and then what is the purpose of behind the building the ontologies. So in the next part, I'll be using a tool to just demonstrate the building of an ontology. Right? So these are a couple of slides that talk about how to build these ontologies, which I'll be talking about while building the tool, using the tool. So I'll again take a pause. So if you have any questions, do let me know.
If the participants have any queries, you can always interrupt in between for this session, because that is making it, Dr. Raghava is making it as an interactive one, and you can always unmute your mic and ask.
Hello, sir.
Yes.
Hello. So can ontology be built for association role mining, like in data mining tasks and so on?
No, so ontologies are mainly used for describing that particular domain, right? So now for association rule mining, you cannot, this is not it's not. I don't think they are related. So, for
Okay,
example, if you want to, I don't know, describe any particular domain, like say e-commerce or things that are placed inside a store, right? So then you can describe those things.
yes, sir. Okay, thank you, sir.
So what about for feature extraction kind of things? From text or some image, I wanted to extract some features kind of thing. Can we build ontologies and from that one can we get?
Right, right. So you can again, so you can use it for any purpose, but the basic point of building an ontology is to describe. So, for example, like taking that example, right? Let's say you want to uh, use the features for I don't know. Let's
For
say
classification kind of thing, like
yeah,
clustering kind of thing.
classification, but yeah, I'm thinking of, let's say, the images, right? So you are given a bunch of images, and now you need to from those images just recognize whether it's an animal or not. So it is a binary classification.
Yes.
So the ontology, you can build an ontology saying that what is an animal and what are the features that make up an animal. So for that you can build an ontology, and you can use it for now you have definition of animal and its features, so you can make use of it in your classification task, in the sense that whichever feature has this characteristic, you can say that okay, now you exactly know what a mammal means, or what animal always has a tail, or it has, for example, eyes and say nails and legs and so on. So you can define these relationships, and then it might be useful for in the machine learning task as well.
So people
Right,
are
but there is
saying
no
that one.
so there are no exact explicit. So if you build an ontology, you will get to know you, in a sense, I mean, the people working on this particular application, they'll get to know it better, the domain, and then what makes a feature. So let's say, okay, you build this machine learning model, right? And now someone else is looking at it. So they might wonder why you have given more preference to the tail, for example, rather than something else. So if you build an ontology, you can say that these are the features that make up an animal, and that's why I have given preference to these features rather than, I don't know, some other features. So in
Okay.
that sense, it's helpful. Yeah.
And the people say that when deep learning always is going to learn the things very well, so why you are wasting the time on building this ontology? In the sense, for machine
Right.
learning purposes, okay, building ontology is that much good or not? Okay, your idea is what?
Okay. So these are two different things, right? So for example, you might have heard of this term called explainable AI. I think that's one of the sessions later on. So in your machine learning model, it's like a black box. So
Yeah.
so you have your data. Let's say you have your tons of data, and then you have the model, and it will make a prediction. But it's very hard to say how it has made the prediction. Right? But in the case of logic and ontologies, it is very explicit on how. So whenever it makes any inferences, it's very easy to say what are the steps it made use of in deriving this inference. So it's, in that sense, it's not a black box. So and the other important difference is it's in your machine learning, it's a variable, right? In terms of the prediction, the accuracy can vary from 0 to 100. But in the ontology, so you can say that with 90% probability, your prediction is right. You can say that, right? But in the ontology, it's very specific. It's 1 or 0. So either you can make an inference which is 100%, or you cannot make an inference which is 0. So there is nothing in between. And that is one of the reasons that helps in having this white box kind of mechanism, right? So it's easy to figure out what are the steps that were taken. So there is a field, there's an emerging field. It's called neurosymbolic AI, right? So where where people are trying to combine both these worlds. So the neural part is obviously the neural networks, deep learning part, and then the symbolic world is what is called as the symbolic part, representation. So you look at things from symbols point of view. So if let's say there's a concept called car, so you can represent car by C and then put it in the ontology. So there is ongoing work on integrating these two fields precisely for this explainable layer. So, if you put in this logic into some aspects of these neural networks, then you can try to explain some of the predictions better.
Thank
right?
you, sir.
Hopefully, yeah. So, are there any other questions?
Sir, in case of knowledge graph and in case of ontology, in knowledge graph,
Right.
you told, sir, it is some kind of collection of some instances.
Right.
So then actually the difference, I didn't get that point actually. Can you please explain again the difference between ontology and knowledge graph?
Sure. So I gave the analogy of, okay. So maybe I'll give the example again. So let's say there is a, so Raghava, so my name is Raghava, right? So Raghava works at Reply Detail. It is a statement or a fact. Now, you can put this statement into a form of a graph. So you can make Raghava as one of the node. The other node would be Reply Delhi. And the relation that connects these two nodes is work set. So Raghava work set, Reply Delhi. So edge here is the work set. So this is a graph now, right? It has two nodes and one edge. So if you associate type information with it, so you can say that Raghava is a type of faculty and Reply Delhi is a type of university. So this conceptual level relations are part of ontologies. So you talk about abstract level details in the form of concepts and relations that goes into the ontology. So in the ontologies, you will have university, faculty, course, and so on. But in your knowledge graph, you talk about these instances, which is Raghava, Triple Delhi, or NIT Kurukshetra, and the courses that are part of these universities and so on. So taking the analogy of object-oriented programming, right? You have your class and the object. So object is an instance of class. So if you talk about the relationships between classes, that is the ontology. And object level data, and then how one object interacts with the other, that forms the knowledge graph. So that's the difference.
Sir, in case of ontology and knowledge graph, which come first? Either ontology or knowledge graph comes first. The knowledge graph means collection of some sentences you told. Suppose X is a faculty of.
Yeah, so no, it's a collection of instance data, right? In the form of a, okay, I'm going to use this term, triple. So you will hear more about this later on. So triple is nothing but the subject, predicate, object, right? So Raghava is the subject, relation here is the predicate, which is work set, and Reply Delhi is the object. So as to which comes first is the, so it's a good practice to start with the ontology and then have the instance data, but that doesn't always happen, right? For example, I mean, not everyone sticks with the good practice. So there are lots of knowledge graphs out there that do not have an associated ontology with it. So some people start from, say, bottom up, as they say, where you get the data, you start first, put this knowledge graph together, and then worry about building the high level data, which is knowledge, which is ontologies. But my suggestion would be to stick to the top down approach, where you first think about what the higher level abstractions are in the form of an ontology. So discuss with the domain expert, build this ontology, and then come to the instance level data.
Okay, sir.
So are there any other questions? Okay, so if there are no other questions, then I'll move on to the
Yes, sir. To the design.
model AVOX and oh, someone is familiar with AVOX. Okay.
Okay, can you model A box and T box in Protege and show us a sample?
Sure. Okay, I'll do that. So we haven't discussed those things, right? So I didn't want to talk about those A box, T box. Okay, but I'll so when we go over it, I'll show it. So this is a tool called Protege. Right? So, and if you type, you'll easily find this on the web. So it's from Stanford, and if in your search bar, if you just say Protege Stanford, you can, the very first link or the top 2 links you will find it, and you can download it. And the installation, there's not much of an installation. It's an exe file if you are on Windows, and if you are on Linux, you would say sh file, .sh file, which you have to run. So it will start up, and so I'll skip a few things and directly jump to this entities part. Under the entities tab, you find these all the things that are of interest to us, at least in this session, right? So you have your classes, the object properties, and the data properties. So I'll discuss the differences between these two later on, but we can start with classes. So the first thing that, at least for this session, that we should decide on is the domain. So like I said, we can keep this interactive. So we can build, we can select any domain, right? And all of you are the domain experts in this case. So we can have, so I'll give a few examples, but you can suggest some domain. So for example, there can be a domain related to a specific sports, right? So for example, cricket, tennis, or sport in general, or you can have...
can family be a domain? Family hierarchy or family relations?
Right, yeah, there can be family, there can be movies, or solar system, politics, transportation. So all these are multiple different domains, right? Or specific, something specific to healthcare. So whatever it is, so you can let me know the domain that you want that we should model now, and then we can get started. So what is it? So should we start with family, or is there something else that is of interest?
Go with movies, sir. Always interesting. Yeah.
Okay. Sure. So yeah, we can start with, so we can model movie. So now you can tell me about, so the next step would be, so we decided on the domain, and like I said, all of you are domain experts. So we'll be interacting with each other, and then we'll be building it. So the first step is to talk with all these domain experts, which in case it's you, and then gather the important keywords in this domain. Right. So for the sake of, since we are short on time, I can categorize these keywords into nouns and verbs. Right. So let us start. So ideally, you just list out all these keywords and then categorize them. But let's just jump ahead and then have a few nouns.
Yeah.
And then we shall also have a few verbs. Right. Okay. So give me a list of five verbs. Sorry, 5 nouns. So if you want, it can be lengthy, or it can also be short.
Yes.
So what is it?
Director.
Character. Okay.
Director, sir.
Oh, sorry, director. Okay.
Yeah. Director. And producer.
Okay.
Choreographer.
Choreographer. Okay. I got the spelling right.
Right, sir. And cameraman or cinematographer.
Okay, all these are right. So you may want to also okay, I'll write cameraman. So the other important set of people in the movie is the actor, right?
Actor.
So you have actor,
and
then you may want to capture the details about the movie itself. Right?
Yes,
so things like, so what is the name of the movie, what is the budget, and so on.
Genre of the movie are kind of
right. So okay, so I'll also list the genre.
Yeah.
Okay, I think that's sufficient for now.
More nouns, sir.
So are there any verbs?
Yeah, dancing or dance or acting.
Okay, acting, yeah, that's good. And then maybe 3 or 4 is sufficient, right? So something like I don't know, has a budget.
Budget, right? Okay.
Or
Box office.
what about release date? We want release date or not? I don't know if it's a. But you can say, yeah, you can. You can suggest more.
Attendance. एक अलग बनाकर
As a story.
एक शीट बना लो.
As a story. Okay.
Copy paste कर लो इसे पूरी को.
Okay, so I think this is good enough to get started.
One के 3 column. Session 1,
One has
session
to
2, session 3.
mute. Okay.
I'm so sorry I interrupted.
Yeah, that's all. Yeah. Okay, so here there are two parts to this one, right? So I'll briefly describe what this is and then we can get started. So you have your OWL :thing. So OWL I already briefly discussed, which is the web ontology language. And one of the importance of OWL is that it's a W3C recommendation. So W3C stands for World Wide Web Consortium. Right?
Yeah.
And so can you give me an example of one more W3C recommendation that you use in your almost everyday life? HTML, right?
Yes.
Yeah, HTML, XML. So XML, yeah, it's harder to figure out, right? But HTML is something that whenever you browse, you come across HTML. And HTML is a recommendation. W3C is recommendation. So the importance of a recommendation is that no matter who implements it, right? So in this case for HTML, there are multiple different browsers that needs to implement the specification. So there is a specification associated with the recommendation, and then there are these implementations. So all these implementations should stick to the specification. So in this case, let's say you have a tag called bold, P, or italics, right? So if you use that tag, then it has to be rendered in a specific way, right? And all the browsers should stick to the same rendering part, right? So if you have bold, no matter if it's Chrome or Firefox or Safari, right? Everything, all these three browsers should display that text in bold. So that's the, and again here OWL is a W3C standards, and there are multiple different software systems that can, say for example, import and export OWL or work with OWL. So all of them should stick with the specification. So OWL here, the first part refers to the namespace. So I'll not discuss what a namespace is. So that comes from the XML domain, right? So that's the namespace, and then the next part is the concept name or the thing. So here it's a thing. So going back to the set world of sets, right? This is the mathematical set. You have something called as the universal set. So if you have these Venn diagrams, you represent this universal set as mu or u, whatever. So universal set is a set of all sets, or in some sense it's the parent of all parents, right? So thing in OWL is similar. So thing is the superclass or the parent class for every other concept, and so whatever you create, it's automatically a subclass of thing, right? So and you can, there is obviously a mapping between the concepts here, OWL, OWL, and then sets, which in turn can be mapped to first order logic. So all these are interconnected, right? Okay. So when we say class A is a subclass of class B, then it's equivalent to saying A is a subset of B. Okay, so let's start with the creation, right? So you right click, or you can click on this icon, whatever is the case, and then you build a class. But before you do that, it's important to have a namespace. So don't use the default namespace, but use any proper namespace, right? So in this case, I'm making use of my institute, ac.in, let's say, and then say FDP, say I'm just using SWeb, and we are building the ontology related to movies. So I'm saying movies, right? So this is the namespace or the IRI, and now let's start building the subclass. So we can go back and look at these, and then build it according. So all the nouns become classes, and the verbs can go in as the properties. So nouns, we start with movie. So as you would notice here, right? Automatically the IRI that we put in there, it shows up. And okay, so this is a sibling. So sibling is at the same level, and subclass is one level lower. So you have actor. So actor and movie, they are at the same level. Let's say you have, maybe we should say crew, right? Movie crew or crew. And as part of the crew, you have all these people.
Yes, sir.
So we can do that just to show the hierarchy. So for example, I create a crew, and then so I can drag and drop. So actor is now a subclass of crew.
Yeah,
we
director.
can have a few more subclasses like director, right? And then producer, and who else? You wanted genre, right? So okay, genre is not part of the crew, so it's
movie, yeah.
So yeah, we'll connect all these together later on. So you have movie and genre, which are siblings, and then within crew you have all these people, right? Maybe we have producer, yeah, okay, cameraman is also crew. So, okay, so I'll leave it here, and let us go for the verbs or the properties. So you have two types of properties here. One is the object property, and the other one is the data property. All right. So there is some difference between these two. So let me go back to the slide. Okay. So so if there is a property that connects a class with or an instance of a class with, say, a constant or a literal, so we call it literal, but take it as a constant, right? Like budget, for example. Movie has budget, and it's a specific number, right? Like 50 lakhs, for example, or 1 crore. And okay, maybe we can stick to 1 crore. The movie has a budget of 1 crore, which is a number. So in this case, student has roll number, which is a particular constant, right? But if you look at the example that I gave, work set. So Raghava works at repeatedly. So it is connecting one instance with the other instance. So both are instance of a class, and it's but in the case of data properties, they are connecting one object with a data, and that's why it's called data property. But in the case of object properties, it connects two objects, right? In this case, it was Raghava, and it's connecting to repeatedly. So that is the difference between an object property and a data property. So now, yeah, let us create a few of these properties, right? So in this case, you can connect, say, movie with the crew members. So movie has actor has director, and has producer. So in that way, you can connect these. And then you can say movie has genre, and you can say movie has I don't know, budget, for example. So let's create a few. Okay. So, but before we create that, I again need to explain about this, right? So there is something called top object property, and then top data property. So it's very similar to your universal class. So thing is what is called as the universal set or the parent class, right? It's a parent class for all the classes. And the opposite of thing is nothing. So it's the negation of thing, but we will not be discussing it here. So in the object properties, you have something called top object property, which is again the parent property for all the properties. And in the same way, you have top data property. It's the parent property for all the data properties. Right? Okay, so let's create a few of these has actor, and then I'll say has genre, and has director. So you can also have has director. Okay, so this is a modeling relation, right? So you can either have has director as a data property and directly say I don't know, movie has director string. So in that sense, you can say Batman or say Dark Knight has director Christopher Nolan, right? Or you can have more information associated with it. So for example, you can say that director is now a class, and there are a few properties associated with the director. So you can have properties like so the name of the director, the his experience. So for example, it can be about his the education details that he had. For example, he might have attended a film school, so you can associate that kind of information with the director. You can also have information like age, if it matters in your application, or I don't know, or maybe the genre that director can be associated with. So you can if you want to have more information, then you can create it as a concept. But if you just want to have a name, right, then you can put it as a data property. But that is a design decision that you have to make while creating this ontology with respect to the application that you have at hand, right? Okay. So the other important point, which actually I missed, is okay, what are called as competency questions. So this is important. Okay, so one of the issues with ontology is you need to determine the scope. So one of the first steps is to first figure out the domain, and within that domain, when do you want to stop? Right? Because creation of an ontology is a never-ending process, right? So because there's a lot of knowledge in the world, and you cannot model everything that is there out there. You have to stop somewhere, right? If not, you will be creating this ontology forever, and it will never end. So just as an example, you can look up something called psych. So psych is a very large knowledge base or an ontology that has been developed over several years. It took several man hours. That means several people were involved in it. A lot of money was put into it. So the idea was to develop one big knowledge base that can capture all the or most of the knowledge in the world. But this project never got completed, right? Because the knowledge it's not limited in the sense that you cannot say that if you have modeled X, Y, and Z, you are done with the knowledge. It's always keeps growing, and then there are lots of things to model. So competency questions can help you to narrow down your scope. So let's say in the case of movie, right, there are again different aspects. So we haven't talked about theaters, for example, or the duration of the movie, the number of screens in which it should be released. So all these things are also part of the movie world, but at least in this case, we said we are not interested in it, right? Because our application does not demand this. So competency questions are a set of questions that the ontology can answer. So these are the minimal set of questions. So ontology can answer more questions, but these are at least the minimal set that it should be able to answer. So in our case, So let's say competency questions can be something like who is the director of a of movie X, for example. What is the genre of movie X? What is the budget of movie Y? So these are who are the actors movie X. So these are some of the competency questions that we can have. So based on this, we'll restrict the scope. Right. So did you understood the importance of competency questions, right? So the first step is to determine the domain, and the second step is to come up with the competency questions. Then you restrict the scope. Now within that scope, you discuss with the domain expert and then come up with the important terms in the domain, and then you categorize them into nouns and verbs. So nouns would become your classes, verbs would become your properties. Right? Then you can start enriching the ontology. So in this case, I haven't connected any of these classes together, right? Except the subclass. There is no other relation between them. So now we can start making those connections. So the first thing that we can do is, let's say, have this domain and range. So for example, a hash director can have domain here, and then I'll expand this. So movie is the domain, and then range should be director, right? Movie has director, right? So the range can be director. So the domain is movie and range is director. And now you can also go back and connect these. So there are different types of what are called as axioms. So axiom is nothing but it's a fact that you can put in the ontology, and that talks about the relationship between these classes. So earlier there was a comment on T box and A box, right? So T box, T there stands for terminology. So terminology again is the abstract term. So it's a conceptual. Whenever you talk about concepts and relations, it's the terminology. A box is the I forgot. It's the annotation. No, it's not the annotation, right? It's the assertions. Yes. So it's the assertion box. So assertions again, it's the instance that talks about the instances. So if you have a particular movie, Dark Knight has director Nolan. So that's a specific instance, and that's the A box. Okay, so let us again create one of the axiom here that connects movie with director. So you can say, so we can say that every movie should have at least one director, right? That's a fact. So let's do that. Let's create that. So every movie, it's a subclass already. So I'll go here. It's an object. Okay. So we want to say that every movie has at least one director. So if you look back at first order logic, right? If there is a term called at least one, so that means if there is an existential. So movie has director, and there is this existential. So I'll not go over the others because we are running out of time. So I'll just go with the existential. So existential means every movie should have at least one director, and it should be connecting to the director. Okay, so this is how you end up with it. So movie has director. So this when you convert this to natural language in English, so you can say that every movie has at least one director. So is this clear? Are there any questions? Okay. So so you can, I mean, we can go ahead and then look at all these, I mean, make domain and range, and then look at these characteristics, which I haven't covered here because we don't, there's no time. And then you can also come up with these axioms. So I'll discuss one more axiom, which is the disjoint axiom, right? So for example, assume that producer, director, and actor are disjoint with each other. That means if you look at it in terms of sets, which they are, so producer is a set, director is a set, actor is a set, right? And the instances are the elements of the set. So, so by disjoint here, I mean that all of them are the intersection between these three is null, is a null set. So that's what we mean by disjoint. So assume that there is no producer, so a movie cannot have the same person as producer, director, and actor. Although in some movies it is possible, but for the sake of modeling, we can assume, right? So let's make that relation, right? So we say that now producer is disjoint with director and actor, right? So if you go here, I mean, that automatically shows up because they are disjoint is a symmetric relationship, right? So if A is disjoint with B, then it automatically means that B is also disjoint with A. So that's why this shows up here. Okay. So I'll wrap up in 5 minutes. So just to give an example of an ontology that is better constructed or fully constructed, so to say, is I take one more case here. I'll leave this as it is. So earlier I built this cooking recipe example for my course. So where we have these different types of cuisines, right? So we modeled the Indian cuisine, and then you have your South Indian, North Indian, East Indian cuisines. And then there's the Mexican cuisine. So for the genre, we can do something similar to what we did for flavor. So there are fixed number of genres, right? You have, I don't know, let's say horror, romance, comedy, etc. But they are fixed in number. So if they are fixed in number, then you can make these what is called as a closed class, in the sense that this class can have only the 4 instances that you have mentioned here. So this is called as a closed class. So flavor can now have only 4 instances, which is bitter, spicy, sweet, and tangy. So it cannot have any other instance. So in the same way, even genre can have only a few predefined instances, right? Okay, and it has a few object properties as well, and a few data properties like calories and serving size. So I'll just show one example of that white box question that was raised earlier, right? So if there is an inconsistency here, you can ask the reasoner to specify what the inconsistency is, and you can fix it. So for example, here I have defined that all these different cuisines, Indian cuisines, are disjoint with each other. So that means there is, at least for the sake of this model, right, assume that there is no cuisine or no dish that is common between, let's say, South India and North India. So let's, so if you want to create these instances, you can click on this individual tab and then create the instances. And this is where you get the A box as well, right? So for example, where is that? Paratha. So let me go here. So North Indian cuisine. So I said paratha is a North Indian cuisine. So now this is what is called as the assertion or the A box part. So you create an instance and you are associating it with one of these concepts. So let's say there is some dish which is common between them. So one of you have created this ontology, and then later on, after a month or so, someone has again looked at this ontology, and they asserted that they created an instance saying that I don't, let's say, I don't know, raita, for example. So raita is North Indian dish as well as a South Indian dish. Right? Or we can create one more. Okay, I'll just add this. it's easier. So let's say there is paratha, and now I'm saying that paratha is also of type South Indian dish. Right. So both North India and now South India have a paratha, but we are also saying that they are disjoint with each other, which is a contradiction, right? So if you have a very large knowledge base, and say multiple people are working on that knowledge base across, let's say, 2 or 3 months. Now, after every 15 days, let's say there are new facts that are getting added to this ontology. So initially you said that paratha is a type of North Indian cuisine, and let's say after 15 days, someone else in your team comes in and says that, okay, paratha is also a South Indian cuisine. So there's clearly a contradiction here, but it's not possible to determine this contradiction, right? So, I mean, in a ontology, you can use this reasoner, and then it will easily figure it out. So it will also ask for an explanation, and this is the aspect that I was talking about earlier. Right? So you can easily explain things in the world of logic, which is what an ontology is, and it becomes very hard to do that in say in the machine learning kind of applications. So here it's saying that paratha is a type of North Indian cuisine and it's a South Indian cuisine. And you also said that they are disjoint with each other, right? And that's why there is an inconsistency. And the explanation has been shown. So now it's up to you to go and fix it. Right? So, okay.
Sir, may I interrupt?
Yeah, so with that, I'll stop. And if you have any questions, I can take them. Yeah, please go on. Yeah, any questions, I'll take.
If the participants have certain queries, please go ahead. Because I think you have explained in such a good manner out of the way from your presentation that how to completely create an ontology with various different types of axioms and even checking the inconsistency with the reasoner. So yes, I hope that is a start for the participants how to create an ontology.
Right. So you can go back and then download this tool and then start exploring it. So there are lots of, like I said, in my slides also I have some references, but there are also lots of material on how to use Protege on the web.
Sir, do you wish to continue for a few more minutes, or I think
no,
because the time is already
yeah, we are out of time, right? So I am done from my end.
Yeah. Thank you so much, sir. I hope it was yeah, really quite informative for the participants also. And we will join back if you people have any queries at some later point of time also. Then Dr. Raghava can always answer the queries by text also. He can reply to my emails, and you can also directly write to him.
Yes.
So thank you so much. Thank you, sir. Thanks for being here with us.
Yeah,
and,
thank you.
We close.
Thank you all. So it was good interacting with all of you.
Yeah, you people can write your queries to him also. So we close the session here, and we will get back at 3 o'clock. And the meet link has already been circulated to all of you. It is inside the session plan itself. So you can join the evening meeting link at 3 o'clock. Sharp 3 o'clock, please, so that we do not run out of time. Yeah. Thank you and bye-bye.
Okay. Yeah, thank you.
Thank you, sir.